It is a literal wave of destruction. Originating deep within the ocean, it poses a seemingly invisible threat until it reaches land. Then, this awesome force of nature can unleash its fury to biblical proportions. This is a tsunami. Is there a way to predict such a massive disaster? What can be done to mitigate the damage of these deadly natural catastrophes? On May 22, 1960, the most powerful earthquake ever recorded struck the city of Valdivia on the southwestern coast of Chile. This catastrophic event was quickly followed by something even more devastating. Ocean waves, some as tall as 25 meters, ravaged the South American coastline, leaving 2 million people homeless and killing or injuring thousands more. The waves also caused major damage as far away as the island of Hawaii, over 10,000 kilometers into the Pacific Ocean. Following this earth-shattering tragedy, Western scientists adopted a much older word for this natural disaster.
A tsunami is a Japanese word for harbor wave. They're really formed by seismic activity, by earthquakes, volcanoes, landslides, things like that. That basically displace tremendous amounts of water. They can travel for tremendous distances, really crossing entire ocean basins, and they move very fast at the speed of a jet airliner, more than 500 miles an hour or 800 kilometers an hour.
Wavelengths can be about 200 kilometers long in the open ocean. That is why people in the sea or even on a boat, you cannot recognize the wave under you. But once they reach to the coast, the wave can increase dramatically. It can be 30 and 40 in the Japanese tsunami 2011. According to the measurements, it can be 80 meters high. So that is a dramatic force.
Historically, the most common cause of tsunamis has been a major earthquake.
In order to generate a tsunami, it is necessary to have a sufficiently large displacement of the seabed. This underwater displacement, following an earthquake, can be related more or less directly to the magnitude of the earthquake.
People use seismometers to detect, because we know most of the tsunami are caused by earthquake. We have a conventional theory, which is we think the earthquake will lift the seafloor up, then that will push the ocean water, so that will cause the tsunami.
A 5.5 magnitude is a threshold at which you start to say that something has happened, but that there is no risk of a tsunami. And then it's from a magnitude 6, where you can start to have very local effects.
The biggest challenge for preventing tragic loss of life in the wake of a tsunami is knowing when and where it will strike and how large the wave will be.
To my knowledge, there's no way to predict earthquakes. We can do probabilistic analysis where we estimate the recurrent rates of a certain magnitude at a certain location over a certain number of years. So we have an idea of the seismic potential of an area and when, on a certain scale, it could happen. But to say that such and such an event is going to take place in such and such a place, with such and such a magnitude, at such and such a time, no, it's impossible.
If you don't even know that there's going to be an earthquake, how can we then forecast that an earthquake is going to produce a tsunami?
On September 28, 2018, French tourist Jean-Marc Pareja, along with his wife Pascal and a family friend, arrive in the coastal city of Palu on the Indonesian island of Sulawesi, never imagining that they are in imminent danger. For them, it is the beginning of an idyllic vacation.
It's a country that we love because of the mentality of the people. Very zen, very nice people, lot of humor. It's also a country where there are some quite extraordinary landscapes. There are 19,000 islands in Indonesia, so there's a lot to explore. This was our third trip. The first time, we went to Bali and Lombok. The second year, we went to another group of islands called Karimun Jawa. And so the third year, it was this trip to the Togian archipelago.
The trio planned to spend the night in a hotel on the beach near Palu.
The hotel is located on the seafront, so outside the city. There is the road that runs along the coast, and the hotel is next to it. And on the other side is the ocean. The hotel is nice. It was a perfectly normal vacation day there.
At 2:59 p.m. local time, a 6.1 magnitude earthquake strikes the Sigi Regency, a few miles south of Palu.
My wife and our friend are leaving for lunch in the afternoon. And at one point, my wife feels her chair move. But she doesn't think it was bad. She was a little unstable and nothing else.
Jafar Bua, a CNN reporter based in Indonesia, also feels the medium-sized earthquake.
Hari itu saya sementara bersama keluarga di luar.
I was with my family outside the house.
Tiba-tiba terjadi gempa sekitar.
And suddenly there was an earthquake around 3 p.m. and we had to stop eating.
Dan kami harus berhenti makan ketika itu.
And after that, we returned home because this afternoon at 6 o'clock, I have promised the committee of the Palu Nomani Festival to cover the event.
Festival Palu Nomani untuk meliput acara itu.
And my office, CNN Indonesia, has assigned me to cover the cultural festival held by the Palu City government.
Yang diselenggarakan oleh pemerintah kota Palu itu.
2018 marks the 10th anniversary of the local cultural festival. At 6 p.m., hundreds of people, including many international tourists, are gathered on the Talise beach for the festivities. Then, at 6:03 p.m. local time,
I'm reading the French press on my tablet. I'm at the hotel reception because the network is a bit better. And all of a sudden, there's a huge vibration. There are a lot of small buildings with tin roofs. So I think of a gust of wind at first. I say to myself, here's a big gust of wind. And suddenly, I realize that there's no wind at all whatsoever. And then it starts to shake. The table in front of me starts shaking. The bench I'm sitting on starts shaking. I understand very quickly that it's an earthquake.
Tapi kemudian tiba-tiba pada pukul 6
But suddenly, at 6 p.m., a great earthquake occurred.
Bahkan para pengendara sepeda
We then left the house as a family, sat on the ground,
Kami kemudian sekeluarga
and took cover looking for a safe place, away from high buildings,
berlindung mencari
because we were worried that buildings would collapse because of the strong shaking of the earthquake.
tinggi karena kami takut.
The shaking is very violent. That is to say, you can't stand upright. Me? I fell on the floor. There is a woman from the hotel who was thrown and fell on her forehead, who opened her forehead, falling to the ground. Everybody falls. Everything falls over. Scooters overturn. My wife, next to her, the ground is sinking, collapsing. And it lasts, it's very difficult to estimate the time, but it lasts 30 seconds, a minute, no more. But it's extremely violent. The noise is deafening, a sort of jackhammer noise, but to the power of 1,000.
The earthquake lasts for less than a minute, but its intensity measures 7.5 on the Richter scale. According to the Indonesia Agency for the Assessment and Application for Technology, the earthquake released 200 times more energy than the 1945 nuclear bombing of Hiroshima, Japan. And for the people of Palu, the worst is yet to come.
Forecasting tsunamis is tricky. It's very different than forecasting hurricane storm surge or coastal flooding that comes from a storm, because with forecasting storm surge, we have the benefit of having days' notice of what's going to happen meteorologically, because a hurricane is the forcing mechanism. With a tsunami, the forcing mechanism is often a volcano or an earthquake. Those are harder to predict. The other reason that tsunamis are difficult to predict is that they can travel so far. So, for example, in the Indian Ocean tsunami in 2004, this started with a massive earthquake in Sumatra. The tsunami traveled for such an extent to the west that it soon outran areas where the earthquake was felt.
The December 26, 2004 earthquake in Sumatra was followed by a series of massive tsunami waves, with some reaching 30 meters in height. Communities on nearby coasts received little warning, and an estimated 228,000 people in 14 different countries were killed, forcing scientists to acknowledge that tsunami warning systems needed a major overhaul, particularly in countries with coastal areas on the Pacific Ocean.
Following the Sumatran earthquake in 2004, studies were carried out to try and find out a little bit about the number of tsunamis per year that were observed in each basin on the surface of the planet. 3/4 are indeed in the Pacific Ocean. There are only 4% in the Indian Ocean. So that means that in percentage terms, there aren't many, except that when it happens, we can have catastrophic events, like the one in 2004, for example. And when we continue to look, Northeast Atlantic, we have about 10%. About 10%, roughly equal of events that generate tsunamis in our areas.
In 2012, the French government agency Senault created its own National Tsunami Warning Center in Essonne, near Paris.
Senault is responsible for monitoring all major earthquakes in the Mediterranean area, adjacent seas, and the Northeast Atlantic Ocean.
France is considered to be characterized by moderate seismicity. That is to say that we are not in a context like the Pacific Basin, where there, because of its large subduction zones with very high convergence spreads, we have events that can reach magnitudes 9 quite regularly. We don't have large subduction zones like that. So we have a moderate seismic activity, but moderate seismic risk does not mean no risk of tsunami.
The strongest earthquakes imaginable in the Western Mediterranean, at the North African margin, which extends from Morocco to Tunisia, could be of a magnitude 7.3 to 7.5. In this case, it has been estimated that the tsunami could generate waves on the French coast that could reach 2 to 3 meters in some areas, or even a little more, depending on the configuration of the coastline.
Scientists at the Warning Center utilized traditional tsunami detection technology while developing new methods for the future.
If a tsunami is propagating, it is necessary to observe it. It is necessary to measure it, and in this case, we use tide gauges. These are devices that are installed along the coast and which estimate the height of water, of the ocean or the sea at a given moment, and which allow us to know if a wavefront is propagating through the ocean or the sea.
The center also processes information from tsunami meters, sensors installed on underwater buoys that can detect changes in pressure as waves pass overhead. In the wake of an earthquake, such changes could mean a tsunami is headed toward the coastal areas.
In the event of a strong event, for example, in the Ligurian Sea between Corsica and France, of an earthquake that would be of a magnitude 6 to 5 approximately, and that generates a tsunami wave, waves would arrive rather quickly on the French coasts.
The tsunami warning for civil protection must be sent within 15 minutes. So in general, the operator, between the moment the event is detected and the moment he validates the parameters of the earthquake, it takes between 5 and 8 minutes.
As part of the efforts that are made to transmit this alert, there are exercises that are practiced between us, civil security, and then local authorities and the populations. The city of Cannes, for example, has put in place a certain number of indications on the edges of ports and then on the roads to find out the best ways to evacuate in the event of a tsunami warning and which points need to be reached to get to safety.
In 2018, Indonesian authorities have their own tsunami early warning system, utilizing seismographic sensors, tide gauges, and tsunami meters. But when disaster strikes, nothing works the way it should. When the rumbling of a magnitude 7.5 earthquake finally stops, the coastal communities of the Indonesian island of Sulawesi are in shock. Islanders know that the worst may be yet to come. Indonesia sits on the southwest edge of the Ring of Fire, the most seismologically active place on Earth. 90% of the world's earthquakes take place here, along this 40,000-kilometer rim of the Pacific Ocean. When one of the largest earthquakes in recorded history struck the nearby Indonesian island of Sumatra in December 2004, it was followed by the world's deadliest tsunami.
We have an earthquake of a magnitude 9.1 to 9.3, a fault more than 1,000 kilometers long, which breaks, and then suddenly, 30 minutes later, we have a 30-meter high wave that arrives on the coast.
Actually, no instrument to measure tsunami in the Indian Ocean. So the earthquake, of course, is a surprise. The tsunami is even a larger surprise.
One thing that was quite phenomenal was the retreat of the sea. First of all, the retreat of the sea of a kilometer. So imagine when we're on the beach, a retreat of the sea during 20 minutes of 1 kilometer. It gives us an idea of the energy, which will arrive thereafter.
In September 2018, something similar happens on the island of Sulawesi.
The Indonesian archipelago area, that is a region between Indian Ocean and the Pacific Ocean. Those oceans just sitting above several complex of the tectonic plate boundaries. So that on the east, you have the we call Philippine Sea plate. On the west, that's the Indian plate. On the south, there's several small plates like the Sunda plate and the Yangtze plate. So all the boundaries converge in that area. They collide each other or slide each other. So it's easy to generate earthquake.
The September 28th quake originates in the Palu Koro strike-slip fault zone, 70 kilometers south of the coastal city of Palu, and emits energy northward toward the bay. Local seismographic sensors detect the rupture and trigger an automatic warning of a tsunami. But the warning goes nowhere.
This kind of event actually is very challenging for the tsunami warning system, particularly for Indonesian government. In that event, they did have early warning after earthquake, but the communication cut off because the earthquake it destroyed the power. So actually, the local people did not receive early warning about the earthquake.
The water was out, the electricity was out. There is an alarm, a siren in the distance, which corresponds to the sirens we have in France for natural hazards. We say to ourselves, okay, there is an alarm. So they're still warning people that something has happened. Even if I think that everyone is aware of what was happening, but there you go, that's all. There is no evacuation order. The authorities are not there. That's it.
The annual Palonomani festival continues on Talise Beach. Most of the attendees have no idea that a tsunami is approaching. At 6:10 p.m., the first and largest of 3 tsunami waves reaches the coast.
Very quickly, we see the ocean that is beginning. We have the impression that it is boiling. It's really a rather frightening impression to see the ocean in a form that we've never seen before. On the spot, it feels like 10 minutes, 15 minutes. But in reality, between the earthquake and the tsunami, 3 minutes. 3 minutes passed. It rushes towards us. It's coming really, really fast. It's really, it's not a slow rise in water. It's really a wave coming at us. The first wave hits the pier, which is in front of the hotel, and it makes a big spray of water. And there, at that moment, I said to myself, there's something there, still a little unconscious, I think, but I said to myself, something is going to happen. And so we decide to move around and get behind the bungalows. So we really didn't think about it. It was more instinct. I have an image of an old man clinging to a tree and being caught in the current, clinging to a tree. And I say to my wife and our friend, there was a tree right next to it, I said. We're clinging to that tree, and we just had time to cling, and the wave came and hit us. The only thing that's important at that moment is to hold the tree, to hang on, not to let go.
3 successive tsunami waves, each between 4 and 7 meters high, inundated the coastal areas.
We are caught up in the water for, I would say, 10 minutes. We were starting to panic a little. We were beginning to lack strength. And then the water started to come down and the current calmed down. So we were able to get back on our feet, and that was it. The worst was over.
Saya belum mendapat kabar apakah tsunami terjadi.
I haven't got any news whether the tsunami happened. But then after a few hours, the tsunami hit Palu Bay. I then checked it.
Tsunami melanda Teluk Palu. Bisa tsunami. Kalau begitu saya harus cek. Saya cek dan di sana
Palu Bay was really sad. The bodies were lying on the road. The carcasses of motorbikes and cars were scattered.
jenazah itu sudah terkapar di jalan, bangkai-bangkai kendaraan.
Many victims on the streets. Some were injured and some died. And I think it's like a little apocalypse.
Ada yang luka-luka, namun ada yang meninggal dunia. Dan saya berpikir ini seperti kiamat kecil, ini benar-benar dahsyat.
There are vehicles that have been swept away by the current, that have wrapped themselves around palm trees. A car that is completely folded in two. Its alarm rings for a while. This is a really bad situation. This is not kidding. This is a tremendous disaster. We don't look any further. We're too caught up in the how are we doing? What do we do now? How do we get out of it? We're not there too much looking at what's around us. It's we have to find a solution to get to safety.
The water has receded, but the community is not out of danger. People in and around the city of Palu continue to face the threats of collapsing buildings, untreated injuries, tainted water, and aftershocks that could potentially cause more tsunamis with no warning system in place. Everyone is focused on basic survival.
It's 6 p.m., 6:15 p.m. Night is falling, and then we have to make a decision. What do we do to protect ourselves? We know there may be aftershocks from the earthquake, the wave. We don't know if there can be others. All the people who were on the coast, they all went up. The whole population of the coast immediately went upland.
Local authorities soon learned that the crisis is equally dire in the inland area of Sigi Regency. Although the tsunami wave never reached that far inland, entire towns have virtually disappeared. In the wake of a magnitude 7.5 earthquake and subsequent tsunami, authorities on the Indonesian island of Sulawesi learned that the effects of the natural disasters are more far-reaching than anyone imagined. South of Palu City, on the edge of the Palu River Valley, the farming village of Petabo is buried in mud. Scientists say the situation was caused by soil liquefaction. Vibration from the earthquake disrupted the loose, saturated soil of the rice farming region, turning the ground into a substance like quicksand and swallowing the village.
Saya saat itu juga belum mendapat kabar bahwa
At that time, I also had no news that in Balaroa and Petabo in Palu City, then Sibalaya and Jonugi in the Sigi region were hit by liquefaction. This was land burial. The land is like water. Melted. It swallows whatever is on it. Even houses of any size are shifted, almost hundreds of meters from their location. The people were then buried in the ground. There were also buried houses.
On the other side of Palu City, the village of Balaroa has also suffered catastrophic losses. Of the development's 2,000 inhabitants, 600 are pronounced dead. Another 1,000 are reported missing. Meanwhile, in Palu City, more than 4,400 buildings have collapsed.
With the night, we didn't see the damage around. We only saw it the next day. But the next morning, I had to go back down to the hotel and everything was destroyed. The whole coastline, all the buildings, the small restaurants, the small shops, They had been cut down by the wave. The road had disappeared. The asphalt had been torn away. It feels like a city after a bombing. There is nothing left. We find ourselves in a sort of community. People who are there and who are in the same state as us, except they have lost their house. There was no more food. There was no more water. They were also looking for their family to see if everyone was alive. So that was difficult.
Disaster management teams from the Association of Southeast Asian Nations rushed to the aid of survivors, providing housing, medical aid, food, and water purification.
I then decided I had to be a volunteer for humanity. Luckily, friends from Jakarta and student volunteers from Makassar came to Palu. We set up a logistics warehouse to accommodate logistics shipments, adult food ingredients, milk for children, Pampers and sanitary napkins. We also prepared a body evacuation team. Another team distributed foodstuffs to affected areas in the cities of Palu, Sigi, and Donggala. They had nothing left, so we felt a little guilty for having them. When we left, we had the impression that we were abandoning them when they were in a really precarious situation.
In early 2019, the Indonesian government reported that more than 2,100 people had been killed, more than 1,300 had gone missing, and an estimated 133,000 had been displaced from their homes. Many of the survivors were injured, unemployed, and suffering from PTSD.
We had the post-traumatic shock when we came back. We are lucky. In Grenoble, we also had a post-traumatic unit at the Grenoble University Hospital. We stayed here for more than 2 months, locked up, not daring to go out. The slightest noise, it scared us to death.
In the aftermath of the humanitarian crisis, scientists studied the disaster itself, hoping to reduce the casualties of similar disasters in the future. But different scientists have reached different conclusions.
2018 Indonesian Palu earthquake and tsunami is a very controversial event. The seismology community has determined the earthquake type and the magnitude. That is widely recognized. It is a strike-slip earthquake, and the magnitude is 7.5. So people don't think this kind of earthquake can generate damaging tsunami because the magnitude is that not big, and it is a strike-slip.
The traditional theory of tsunami genesis supposes that tsunami waves are created by the vertical movement of underwater land. In an earthquake, this type of movement occurs when a normal or reverse fault ruptures. However, the 2018 Palu earthquake originated on a strike-slip fault, where the movement of tectonic plates beneath the Earth's surface is side to side.
Strike-slip, that means the two plates moving toward each other, slide each other. It does not generate a significant uplift. That is, does not fit the traditional theory of tsunami genesis. So people immediately think it's a landslide caused that tsunami.
Scientists from the Port and Airport Research Institute in Yokosuka, Japan, theorized that liquefaction might have caused landslides in the coastal areas surrounding the Palu Bay. According to their study, large masses of soil collapsed in the Palu Bay at 9 different locations, and water displacement contributed to the overall energy of the tsunamis. Landslides, including submarine landslides, are a commonly acknowledged cause of tsunamis around the world. including one significant event off the coast of France. Some scientists still argue that there is insufficient evidence for the landslide theory of the Palu tsunami's genesis.
Several research papers mainly using we call modeling approach to test that hypothesis. Actually, after the events, there's several teams we call international science team or national team in Indonesia to survey that area. None of the team actually find convincing evidence of landslide. There are some areas have landslide signals, but those landslide is very hard to generate that powerful tsunami.
Other scientists, including those at NASA's Jet Propulsion Laboratory in Pasadena, California, have been testing new alternative theories of tsunami genesis, focusing on the 2004 Sumatra quake.
We have satellite data seeing that tsunami and also seeing the earthquake. According to the conventional theory, if the seafloor uplift causes that tsunami, so there will have a gravity anomaly at the fault area. So that anomaly is supposed to match the ocean volume that causes a tsunami, which is measured at the surface by another satellite.
In order to mitigate the effect of disasters like the one in Palu City, scientists are rethinking their understanding of tsunamis and using new technology to change how the international community responds to them. The 2018 Palu earthquake caused thousands of deaths and hundreds of millions of dollars worth of property and economic damage. It also left scientists wondering how the quake triggered such a massive tsunami. What unseen circumstances produced this deadly wave? And will events like this be more common in the future? To answer these questions, the scientific community is looking beyond the traditional method of predicting tsunamis based on earthquake seismology.
So as we know, seismic data, you can detect the earthquake location and earthquake magnitude. But unfortunately, the earthquake magnitude is not a good predictor of tsunami size. Or some small earthquake can generate big tsunamis, while some large earthquake did not generate tsunami at all.
Indonesian authorities were unable to predict the scale of the tsunami that struck Palu City. The government had 22 tsunami meters situated in open water, but none of them were operational in 2018. The nearest tide gauge was 200 kilometers away from Palu. Even before 2018, the international scientific community recognized a strong need for a more comprehensive tsunami tracking system. After the 2004 earthquake in Sumatra, researchers at NASA's Jet Propulsion Laboratory began studying data provided by existing GPS tracking systems as well as satellites in space. They realized GPS data could detect precise movement of the land, while satellite data could show the exact location of a tsunami at a given time. Using data from these sources for the Sumatra quake, scientists developed a new theory of tsunami genesis.
The main issue, I think, is the forcing mechanism. How the earthquake forces the ocean to generate that monster wave. So that is the question we're trying to understand. We think the horizontal motion of the continental slope caused by that earthquake is contributing to a force to that tsunami. There's only two kinds of energies. The first, we're talking about the vertical motion that only gives ocean the we call potential energy. But if you have horizontal motion, that we call kinetic energy. That is energy is very powerful. That is why we see many of the large tsunamis generated near the coastal boundary or with a steep topography.
The theory applies to the Palu earthquake, which occurred on a slip-strike fault with the horizontal movement of tectonic plates.
So one set of plates push the water into the bay from south, but another plate push the water from south to north out to the bay. So these two energy overlap causes that tsunami that directly hit to the Palu city at the end of the bay. Because the energy all combined inside the bay. So the energy have to release somewhere. That is why it's so powerful. That is why so many people die in that city.
The theory not only helps to explain historical events, but also to predict similar future disasters.
Theoretically, the tsunami has a precursor. It is caused by earthquake or landslide or if whatever the volcano as a source of that tsunami. So that means theoretically we have time to do early warning. The key is how we can use technology.
The speed of a tsunami is fixed within an ocean. If there is a big earthquake that generates a tsunami at a given place, we know exactly at what time it will arrive. Where it is more difficult to be sure of the impact is the effective wave height at the time of the arrival at the coasts.
GPS can detect land movement, which can be inversely calculated the seafloor motion. So that means that data can be used for tsunami early warning. Since then, we get NASA support to test the real time GPS, because for tsunami early warning, you have to get real-time data.
In addition to real-time earthquake data, accurate prediction requires a comprehensive knowledge of vulnerable coastlines around the world.
In order to be able to model the impact of a tsunami on the coast in detail, we need to have a good knowledge of the topography, whether it's the topography on land or the topography at sea, which is called bathymetry. On the French coasts, we have a good knowledge of this data, but in other regions of the world, there could be a gap. And as a result, it's more difficult to model the events in these zones.
There is a lot of work being done on this very issue. There are areas of research, whole sections of reflection and research on this subject to refine the most exact estimate of the height of the tsunami at the coastline.
I'm working with we call smart cable community, trying to put sensors on the ocean bottom cable. That is the cable for our world, for the internet communication. That sensor can be detect earthquake, detect tsunami, also detect the ocean change, immediately send to the internet. Because we actually can calculate the tsunami travel wave in the ocean based on topography. We can predict those tsunami arrival time and even the tsunami power quite precisely.
Accurately predicting a tsunami is only half of the challenge. International partners also need to create an early warning system that can instantly and effectively deliver the warnings to anyone in danger.
To do that, we have developing we call mobile tsunami warning system. That means we will put the warning system into your smartphone. So if there's an earthquake occur around you, then we'll give you an alert.
Even as technology improves, some worry that tsunamis might become a more frequent danger in the future. With climate change producing more and more extreme weather around the globe, we could potentially see more tsunamis triggered by non-seismic events.
There can also be so-called meteo tsunamis, when there are very strong depressions above the ocean, and this depression moves at a certain speed. Not too far from the coast, there is a bulge in the sea level, and on the front of this bulge, there can be waves which are generated and which finally devastate the coast with tsunamis.
Climate change impacts different parts of the world in different ways. In the Arctic and in the Antarctic, we see a lot of melting sea ice and melting land-based ice and glaciers as well. You can think of the heavy weight of tremendous amounts of ice on land. When the ice melts, the land actually rebounds. You can think of this, if you lay on a mattress and then you suddenly get up, the mattress is going to take a few seconds to really quickly raise up as well. That's what's happening to the land. When we melt glaciers on the land, we get this, what we call rebound, basically the land pushing up.
So some of the ice cap can be actually fall to the ocean, or we sometimes call ice quake. So earthquake, so that means the ice shelf, almost like a tectonic plate, can be break apart, then fall to the ocean, or force ocean water. So that can generate a tsunami too.
Facing an uncertain future with extreme weather, coastal communities are taking extreme measures to minimize the catastrophic tolls taken by tsunamis.
Protection against tsunamis, in the physical sense of the term, ultimately preventing a wave from approaching the coast, is quite possible. In Japan, they have built dikes all along the coasts and harbors so that tsunamis of certain height cannot reach directly inside cities or ports.
These constructions, at least for a certain number of them, have shown their effectiveness, particularly in the case of the 2011 event. Notably in Kamaishi Bay, where we have photos before and after, so before the tsunami and after the tsunami. And we see that the tsunami, because of its devastating size, destroyed a good part of this dike, but it also helped to slow down the impact of the waves in this bay.
Such prevention methods impose exorbitant costs and require local governments and environmentalists to agree on the benefits and potential risks. In Palu City, for example, a high coastal breakwater could cause problems for the fishing industry and threaten to change the local environment and the local culture more than any tsunami. Scientists at tsunami warning centers around the globe say that the best advice for those living in vulnerable coastal regions is to be aware and be prepared.
Very often, when there is an earthquake that generates a tsunami behind it, and we have videos of the area when the tsunami arrives, we always see people staying put and not taking shelter. This means that there is a continuous effort to be made in terms of prevention and risk education for the population.
If you are close to the coast, if you feel an earthquake, the best thing to do as a precaution is to take refuge further inland, high up. Then, if you haven't felt an earthquake, but you see an abnormal retreat of the sea level, that is to say, for a period a little longer than a classic wave, it's a sign of a tsunami, and there, it is imperative you go to shelter further inland and higher up.
Sebenarnya ada pertanyaan orang, kok
People think that this is an infrequent earthquake,
pertama mereka menganggap ini adalah bencana
so they are
biasa.
still in that place. So many victims.
Sehingga mereka tetap berada di tempat itu sampai kemudian tsunami datang. Ada
Then,
pula
how about the warning from the authorities, such as the meteorological agency?
dari lembaga berwenang
I am sure that it will not reach the hundreds of thousands of residents in Palu City.
Palu. Itu saya yakin tidak akan sampai seluruh
Not until the warning, there has been a tsunami,
Palu belum sampai peringatan itu kemudian
so that many people die on the coast of Palu City.
sehingga banyak korban jiwa masyarakat di sekitar pesisir Teluk Palu.
This is indeed a devastating disaster, and we don't expect it.
bencana yang dahsyat yang tidak bisa kita sangka-sangka. Saya harus tetap di sini. Saya bekerja di sini.
I still stay here. I work here. I grew up here. My family is here.
Kemana-mana. Yang kita harus cari.
That's why I'm not going anywhere.
Cara menghadapi bencana-bencana itu setelahnya.
What we have to look for is how to deal with that disaster.
Ketika terjadi tsunami, ketika terjadi.
We have to prepare ourselves how to deal with earthquakes, tsunamis, and liquefaction.
Bisa kita lakukan.
We want to go back to Indonesia because we love this country. We want to see the people who helped us again, because we had a lot of human experiences like that on the spot. People with whom we stayed in contact. And the only way to go back there is to get rid of the anxieties, the fears, and the anxieties that we may have to go back to that place.
In the meantime, an international community of researchers and governments around the globe are working hard to make this seemingly invisible threat more visible and less threatening.